Before going to understand the standard definition of Euclid's division lemma, today we are going to take a few arithmetic long divisions as have been done in our earlier classes. Here are some examples. See, example 1, 17 to divide by 3. Example 2, 17 to divide by minus 3. Example 3, 1 is to divide it by 2. Okay. So let us see one by one. See the first case. When this 17 is divided by 3, we are getting the quotient 5. And as a result, 3 is a 5 equal to 15. And 15 is subtracted from 17 remaining 2. And we know that this is called dividend, this is divisor, and this is quotient, and this is called remainder. All of us know in the previous classes. And also we have seen that this dividend is equal to the product of the divisor and the quotient plus remainder. See here, dividend is equal to product of the divisor and quotient plus the remainder. Is not it? Very clear it is. Okay. Come to second example. 17 to divide by minus 3. So 17 take minus 3 and divide it. So as a result we get 17 is divided by minus 17 is divided by minus 3. As a result we get minus 5 quotient and it is given 15. Then 17 minus 15 equal to 2. Again this 17 dividend is equal to divisor into quotient plus remainder. See that 17 equal to minus 3 into minus 5 plus 2 means this remainder equal to minus minus plus 3 is a 5 equal to 15 plus 2 equal 1 to divide by 2. Here uh, dividend is smaller than the divisor. Okay, see 1 is less than 2, so we are putting 0.1. Okay, then adding 0 here, so that is 10 and 2 goes 5 times. Okay, so 2 into 5 equal to 10. So 10 minus 10 is equal to 0. Remainder is 0. Again here you see that this originally it was 1. Okay, and this is the thing 1. Okay, 0 we have added for this fractional. So see that 1 is equal to 2, this 2 into this quotient is equal to 0.5 plus remainder is 0 plus 0 equal to 2 into half, because 0.5 is half plus 0 equal to 2 cancel and 1 remaining, and then plus 0 means equal to 1. Okay, now we are going to denote the dividend, divisor, quotient and the remainders respectively by A, B, Q, R. We can write A is equal to BQ plus R. 17 equal to 3 into 5 plus 2 implies that this is the thing. Okay, A is equal to BQ plus R can be generalized for different numbers. Instead of 17, many other things. Instead of 3, many other things. And as a result, 5 and 2 will be changed. Okay, so similar is the case for the other two examples. You see here. Okay, we can write A is equal to BQ plus R, A is equal to BQ plus R, where A, B, Q and R stand for the respective symbols. Okay, here A is equal to 1, B is equal to 2, Q is equal to 0.5 or half, plus R is equal to 0, like that. Okay, now it is time to understand the simple version of Euclid definition lemma. As I am explaining to you, not exact definition but the simple version, if we translate them in a simpler manner. So this is the thing, EDL, Euclid's division lemma in simple version with graphics. So first understand the statement. For any two positive integers a and b, there are two more whole numbers q and r satisfying the relation a is equal to bq plus r. comma, r is greater than or equal to 0 but less than p. What he says here, we know that positive integers, set of positive integers and set of whole numbers come here to understand with the help of number lines. Look at here, this is a number line. Towards the right 0, 1, 2, 3, etc. all are positive. Only 0 is neither positive nor negative. And towards the left all are negative. Okay. So Euclid is saying that A and B in the previous relationship here, what is given by those same previous relationship as we have seen here in each of the cases. Same thing Euclid is also saying, but with some restriction. Okay, so here he says that A and B must be starting from here from 1 and rightwards. So for example, from 1 starting, A is equal to 1, 2, 3, 4, etc. up to infinity, and B is also like that, positive 1, positive 2, positive 3 and so on. But Q and R can take 0 value also. So generalize that there can be Q can be 0, 1, 2, 3, 4 and up to infinity. R is equal to 0, 1, 2, 3, 4, up to infinity. Okay, this is the thing what he says in his statement. For any two positive integers, this is equivalent. There are two more whole numbers Q and R satisfying the relation A is equal to BQ plus R, such that R may be equal to 0 or greater than 0 but must be less than B. And this is the graphical interpretation. Now let us understand what is the difference. Now we have seen that this first example is well satisfied. 17 and 3 are positive numbers. Okay, and then as a result of division we are getting 5. This is also positive, and this belongs to whole number. R is also 2. It is from 0 to rightwards. Okay, and satisfying the relation such that this 0 is less than or equal to 2 but less than 3. You see that 3 was the divisor B, less than B, but 2 is greater than 0. It is satisfying. So next cases, see that here it does not satisfy this relationship. See here A is equal to 17. No doubt it is a positive number, but Q and B is minus 3. So it does not satisfy because Euclid is showing like that. Actually Q must be like that, cannot be any negative number. So this is not valid here, but for that actually in general algebra it is valid. Okay, in general arithmetic it is valid, but in Euclid's definition it does not valid. So next one actually we see that it is valid for the dividend is equal to PQ plus R in the pattern of arithmetic long division, but by Euclid's division lemma definition it does not hold good. A is equal to BQ plus R, where Q is equal to Q is fraction, but Euclid does not allow any fraction. Q is equal to 0, 1, 2, 3, etc. No fraction is possible. Whereas in this we have seen that 0.5 means this 0.5 is lying here. It is lying between here. Okay, here a fraction, but here not allowed in this expression. All must be integers. Okay, so this is the difference actually, whereas this is true but not true in this case. So it is also not valid in Euclid's division lemma. I hope you have understood the basic differences. Now let us come to the standard definition. Euclid standard definition. For positive integers a and b, there exist integers q and r satisfying the relation a is equal to pq plus r, comma, r equal to or greater than 0 but less than b. This is the summary of the Euclid's division lemma, and this is the standard division. Okay, I hope that you have understood. This thing you have to remember because it is very useful to prove certain properties of integer numbers as well as to find the HCF in many complex cases. Thank you for watching.